welcome to our first research spotlight with Kilian Lieret. Kilian is currently an AI research scientist at Meta Fair. Previously, he was at Princeton and has a long resume of all the things that he's done before, but I think very impressively, he's in the open source code space. He's done a lot of great things in terms of benchmarks, which we'll talk a lot more about today. But just for a bit of context, if you've ever heard of SWE-agent, mini-SWE-agent, CodeClash, program, all of the above, these are all amazing things that he's worked on. So without further ado, Kilian, feel free to take it away.
Yeah, thank you so much. First of all, it's a pleasure to be here, even though I'm just speaking virtually. I would love to spend more time at AGI House, to be honest, but I'm here in New York. But very excited to talk about benchmarking, agentic AI, and specifically about how I think there should be a paradigm shift and we should try new things to push AI even more than we have so far. So this talk will have roughly 3 parts. The first one is just a little bit of background of where we came from with software engineering benchmarks, talking about HumanEval, talking about SWE-bench, and talking about what limitations they maybe both share. And then there's 2 examples for projects that I've worked on that kind of try to go beyond this very task-oriented nature of SWE-bench. The first one being CodeClash and the second one being ProgramBench. So starting with a quick timeline. So on the left here, that's 5 years ago now, 2021, we had HumanEval from OpenAI. And essentially what that was a code completion benchmark, if you want. So the task for a language model was you give it a function signature and some basic doc string. For example, the task might be, this is a function, you give it a list of integers, square them all and add them together. And then the AI would go in and actually, fill in the function body with, I think it was all Python actually at the time. So it's a very simple specification of a problem. It's very clear what the solution should be. And it's also, and this is the really nice thing, it's very easy to validate if it's correct, because we can just have a lot of unit tests testing that, for all the inputs that we imagine this function to have, we get the right result. So right now, nicely in the middle of this timeline is SWE-bench, which was, in some sense, a big step up in what we asked language models to do. So for SWE-bench, the task is essentially a GitHub issue, a real-world issue in a large open source code base. So the input is the issue text and then also the entire code base at the time of the issue. So the language model would have to localize, what to change, make the changes, and then hand them off in what basically would be a pull request. Now, this at the time was actually considered to be extremely challenging, so challenging that I think most people didn't want to work on this at all. And it took several months and 2 projects to come out to really show that this was possible with the models at the time. First, Devon made its announcement, came out of stealth, and they showed numbers on SWE-bench, which for a certain subset of SWE-bench were around 20%-ish resolve rate. And then also, my team had been, so my background is actually AI for physics, and I pivoted to NLP around that time. And when I joined the SWE-bench-SWE-agent team, and they had been cooking for quite some time and were able to have a similar but open source coding agent at roughly the same time as Devon. I think the release was 2 weeks later, also solving around 20% of issues. But that basically, pushed open the gates of giving language models not only small code completion tasks, but giving them real world issues to solve in an agentic manner. And from there on, it actually took another more than 6-7 months, maybe even more longer, until we had Claude Code. But what I want to say with this SWE-bench, with this timeline here, is that SWE-bench is now as old as HumanEval was when SWE-bench came out. So it's been around for a time, and as many of you probably know, it's also quite saturated at this point. So the Mythos results from Anthropic are at the 90% mark. So the question is, if our current benchmarks are getting saturated, what do we do? Obviously, like this is a very, very biased, timeline. There have been a lot of benchmarking projects and a lot of other projects. But what most people have been doing, and maybe that's a little bit of an unfair summarization, but there was a lot of search for just finding harder tasks. So you kind of stick with the same paradigm of a SWE-bench, but for example, you try to find the hardest issues, or you try to use closed source instead of open source repositories, etc. Or you would just grade the results of the language models in a stricter way. For example, you could have code quality rubrics, or you could try to tighten down the unit tests and so on. But I think what we're seeing is that all of these variations or harder subsets, they are also saturating quite fast. So I think it's time for a paradigm shift of trying to come up with the next step of the evolution of benchmarks for coding. And to kind of demonstrate kind of in which direction I think this should go, a short comparison between let's call them traditional benchmarks, similar to SWE-bench, and where I think we should be going. So most of these that we have seen so far are similar to SWE-bench, very task-oriented or spec-oriented. So you give the AI a very specific problem statement. For example, it might be a stack trace, and then the AI has to go in and fix that very specific error within a very big code base. Or if you're more into the repository from scratch tasks, you would, for example, specify, you would compile a very long document outlining, what all the functions names are, what every single part of the code base should look like, and then ask the AI to implement that. So the challenge here is very much how to implement things. So the AI has to go in, find some context, localize, where the issue is coming from, make some edits, and then write some tests to maybe self-tests, and finally hand over its solution. Now, the nice thing about this is that we can score this very precisely and easily with unit tests, because we have a very clear spec to work with. However, I would argue that actually, in some sense, humans are operating on a very different level, because usually, as humans, we don't really, care so much about very individual issues. We are very motivated by high-level goals. For example, we might want to earn more money, or we want to cure a disease or prove a mathematical theorem, etc. So for these type of problems, the challenge is not how to implement something, it's what to implement to begin with, right? So we start from ideas and experiments, small prototypes, and we iterate them and so on. And only once we have that, we can really dig into the implementation of anything specifically. Now, the real problem with this, it's very easy to say this, but the real problem for benchmarking is how can we score this? Because as I already mentioned, one of the nice things with the spec-oriented or task-oriented workflow of benchmarks is that unit tests usually pre-exist, or they're easy to write, because everything it's very clear what the expectation is. So the rest of this talk will be two examples of projects that I've been working on, where we move towards high-level goals, meaning that scoring becomes more fuzzy and it's more challenging to construct these benchmarks. But I think we're moving closer to operating similar to how humans do. So the first one is CodeClash. So this one I did together with John Yang, who's also at Meta and also a PhD student at Stanford, who had this, I think, very, very cool idea that this is a competitive benchmark. So we are pitching two language models against each other, and one of them will win. But unlike previous things, it's not like the language models are directly playing against each other in some kind of game, but rather we have both of the language models develop a code base. They might start from scratch, or they might start from some demo, but once they're done with a code base, they hand it off, and the two code bases, they compete in some form. So for example, like both these code bases might be a trading simulator, and then you plug them, or like a trading bot, and then you plug them into the trading simulator, and one of them will make more money. Or as you see in this picture, this is more like of a like spatial dominance, or like claim as much land as possible, resource management type of game. So, like the tagline says it all, like the models write the code and the code competes. So in a little bit more detail, like just to kind of dive into how this really looks, we essentially structure that benchmark in two phases, and they repeat several times. So there's an edit phase where on the left you see like you have the two language models, and they operate in some sort of virtualized environment, and they can really do anything they want, right? Like they can run analyses, they can run like the game themselves, like they can look in the internet, like they can do anything. Actually, we might block internet because of cheating pretty soon. But anyway, back when we ran it, models didn't try to cheat so hard. So they could even browse Wikipedia or Stack Overflow or whatever they wanted. The only outcome that they have to deliver is one bot to play, or their code base to play in that competition. Then we run the competition, there's a winner, and there's also a lot of artifacts. We want to play this in multiple rounds, so we want to communicate to the models kind of what has happened and why one of the models has won and one has lost. So we collect gigabytes of logs, essentially, of how this game or competition has played out, and we hand it back to the models. And what makes this so cool is that they can now iterate on their own solution, and they should really dig in and understand what went wrong, like why they lost the last round, for example, and then improve the model. So it's very much like some very targeted auto research, or like research self-improvement kind of loop. And here's one specific example. I don't know which game it is that's playing here. But you see two models. You see Sonnet 4 against Gemini 2.5 Pro. So we ran this half a year ago, so the models are not completely up to date. But what you see in this graph is basically a score for every round. So a round is one of these edit to competition like pairs. We have 15 of them. That's what we use when we ran the benchmark. And you can see actually that the winner might very much change. So initially here, Sonnet was dominant, then Gemini caught up, then it was like a lot of back and forth, and essentially in the end, Sonnet became dominant again. So I think that's already very interesting, because it first of all showed that both models here really tried to improve and did improve, and there were some toss-ups, but in the end you had one model clearly having the better solution, and the other model couldn't even kind of recover and catch up. Just to flash the results we had from the paper, again, this is half a year old, but because it was a PvP benchmark, the score is ELO numbers, just like in chess, which makes them a little bit also harder to update, because you have to play at least like a subset of these model competitions against each other. So John is right now trying to, or working on actually a slightly more simplified way of evaluating this benchmark, and there's going to be an update, I think, next week actually, so stay tuned. But coming back to like the big picture, like why is this so interesting? First of all, like the objective is very open-ended. You can have almost anything that's an objective function that allows you to declare a victor. And you also have this component of adversarial adaptation, right? So one model can observe what happened in the previous round, can observe what its opponent does, and can adapt its own strategy to that. And very specifically, so I already mentioned that like it's kind of a self-directed improvement benchmark, but very specifically, we reset the conversation, or like the agentic history of every model at the beginning of every round, but it can leave itself nodes from the previous round. So the model very much is in charge of kind of what memory it hands over from round to round, or what analysis tools to build. So the model can not only try to improve very specifically the bot that it submits, but it can also improve its own tooling to do so, or like tooling to run simulated versions of the game, etc. How general is that? So I showed a lot of pictures of games, but that's mostly because they're like more fun to look at. So Battlesnake is on the left, and Robocode is kind of like a tank battle. But really anything with a measure objective goes. And there should have been a small overlay here. We recently added a lot of games to it, including some trading simulators, for example. And we also have things like poker and chess that have like very clear monetary value. So I really think we're just scratching the surface with what we already have in the benchmark. But going back to evaluating language models and like the scores they get, one thing I want to point out is that models are actually terrible at this. So this is just one example. I know it's a little bit of a wall of text. But this is for one example called Robot Rumble, which is actually, I think this, no wait, that's Robocode. It's like a robot battle, if I remember correctly. But we found a human leaderboard with a lot of human solutions. They also had ELO values attached to them. And we found one specific solution from GigaChat, that was the username we submitted it. So we were thinking about like, how do model solutions compare against GigaChat or any human really. So we ran more than 10 repetitions of this 15 round things. We really tried to give the models a chance. So I think back then we mostly tried with Claude 4.5 Sonnet, which was the best in the model PvP thing. And essentially the model never won a single round. So like there was a total of 150 rounds, and the human solution, which didn't even evolve, right? Like the model could have adapted to this human solution, but the model just completely failed to even win a single round. So in CodeClash, human solutions are absolutely dominant. Models are not doing well, and that makes it a fantastic benchmark to hill climb on. So the question is like, why is AI so bad at this? And there's a lot of specific things we saw models struggle at. One is to picking up after a round. So they made some edits, they handed off the code base is competed, one of them lost or not. And then we tell it like, this was the outcome of the last result, here's all the logs, try to improve. But models are kind of like behaving like, I don't know, you or me when I was, I don't know, in high school and learned to code, and, I didn't know how to use Git. And so, every time I made a new version, I copied it over into a random document, you ran it, like they just kind of produce like this utter mess when they try to improve. They write bloated code. They don't typically try out completely new approaches, but they are much more stuck in these like incremental improvement loops where the incremental improvements are oftentimes not even fully grounded in the logs. Like oftentimes they would like pull up a log file, read the first 5 lines, speculate on what was wrong, even though the log didn't show it, and then just go on to make random changes. So I think this really surfaces a lot of things of why I think AI auto-research in practice oftentimes doesn't work. And that makes me pretty excited for improvements. Just to show some example, like this is what I mentioned with like model code bases getting bloated. So on the right side, I forgot which model this is, but like this is actually the code base of the model after a couple of iterations, probably after the 15 iterations. And you see, like there's scattered MD files, you see like all these analyze losses, analyze around 13 v2.py, and a bunch of versions of its own submitted code, but there's no kind of logical structure that's kind of converging anywhere. And this behavior was actually really bad with the Anthropic models when we tested it. So that's what you see in a little graph on the left, which is the number of throwaway files they create per round. That means like files that they create and then never look at before. So Sonnet 4.5, which we tested, created like 18 throwaway files per round. So, and then you run it over 15 rounds. So it got messy quite badly. And the other thing, and it's a little bit too much content on one slide, but if you read the paper, it has a little bit more context, is what I previously mentioned with the groundedness of edits, that models loved to look at logs, but they never really tried to fully understand them, or like they oftentimes didn't really base the edits on what they saw there, which again, it really depended on the model. Some models also just don't look at the logs, and so they just make random edits. But this whole interpretation of what went wrong in a complex scenario was absolutely lacking. So that's this last slide on CodeClash. Again, there's going to be updates next week from John, who has been driving this. But I wanted to bring this up as an example of a benchmark that's not going to go saturated, because it's model versus model, and also one that's highly correlated with a lot of very practical applications in terms of self-improvement loops, etc. Obviously harder to evaluate on than SWE-bench, etc. But I think this is kind of where a lot of future benchmarks are probably gonna sit, like in this kind of competitive area. Now, the other project I want to briefly flash is called ProgramBench. It's much more recent. I think we released it like 2 months ago. And if we were to go back to this slide I showed of like this kind of traditional task-oriented benchmark versus the more goal-oriented benchmark, it sits a little bit in the middle ground. So tagline is can language models rebuild programs from scratch, and that's kind of like the vibe we're going with. And again, this was John's idea, and John and me, we built this together at Meta. So the idea here is, let's look at the left at the black box. Basically, the task for model is you give it an already compiled executable. So, for example, ffmpeg, or like any kind of like, let's say, terminal CLI program, together with, it says docs here, but really it's just the README. And the task for the agent is to, look at the executable, like try to find out what it does exactly, and then build you the source for an exact copy. So in order to do this, and this is where this kind of very much differs from like previous from scratch benchmarks, is the agent doesn't really have complete specs of what needs to be built. Like it basically only has a README that says, for example, for ffmpeg, it says, this is a CLI that converts videos or transcodes videos, etc. Or for ImageMagick, or like any kind of like CLI that you might think of. So in the first step, the agent has to invoke the binary to understand exactly what it does. And then when it starts to implement its own copy of that, it has zero guardrails. Like there's zero structure that has been given to the agent. Like it can even pick, whatever programming language it wants. Like it can use Python, which is very popular with AI agents, even though it oftentimes doesn't really make sense. It can use Go, Rust, Haskell, whatever it wants to do. And then it rebuilds it based on its own architecture, which is a component that's oftentimes missing in a lot of other benchmarks. So that's kind of how it looks like from the agent perspective. Now, the tricky part with this benchmark, and which makes this benchmark much more difficult to construct, is how can we actually evaluate the solution? And for this, we essentially we can only use behavioral testing, because the model, it might literally use any kind of program language that it wants to use. It can name things as it wants to do. It can define arbitrary classes and so on. So the only way we can test this is basically we take the executable that the agent builds, and we have tests that we generated based on the original executable that only kind of test input-output pairs. So the biggest effort in this benchmark was really to come up with these tests. Most of them are automatically generated. also from other language models, but it's very tricky to get challenging tests. There's also a lot of fine print, like there's a lot of ways that the agent can cheat that we need to close to make this an interesting benchmark. And one that I just want to already mention here is that the agent cannot decompile the executable. Like the idea here is that we want to give this very kind of opaque spec to the agent, and the agent almost has to like interact with it like a product manager. It has to be like, what happens if I do this? What should happen then, etc. So the agent cannot decompile in any way the program, because it technically doesn't even have read permissions to it. So that's an interesting technical detail. And the other very cool thing is, this was the first results that we shared, that models are this is still extremely challenging for models. So what you see here in dark blue is the percentage of fully resolved tasks in that benchmark. So the benchmark has 200 tasks, and when GPT 5.5 came out, not even on its default reasoning mode, but on the high and X-high reasoning modes, it solved the first instance completely on ProgramBench. So since this is validated with so many unit tests, you can also slightly weaken your definition of what it means to fully solve a task. And we have like this more than 95% of tests pass metric. And there you can see that it actually, very nicely orders models in terms of capabilities. So there's a lot of different metrics floating around with ProgramBench. This is the one that we think is the only one that makes sense, like looking at fully resolved, or while that's so low, at like almost resolved. There's more FAQ on their website if you're interested in like the questions of metrics. We are also now open for submissions. So if you have, for example, an agentic harness that you want to test, you can submit your results on ProgramBench on the website. And it's actually one of our goals that we kick off more agent harness innovation, because unfortunately, for better or for worse, most benchmarks have single agents pretty much outperforming or performing on equal grounds with multi-agents. So even though there's so much hype with multi-agents, there's really not that many ways we can test them. We do believe that on ProgramBench, possibly multi-agents will have an edge. If you're interested in that, you can look in the Anthropic system card since Opus 4.8. They ran tests with varying results. So like even there, it's not completely clear that multi-agents always outperform, but I think with Mythos, I think they had like a slight edge. There's also, I think this might be too much of a rabbit hole here. There's very fine-grained signals you can get from ProgramBench. This is my favorite plot. It might take a second to understand, but what we see here basically is every line is a different model. We have the 200 instances on the y-axis, and on the x-axis we see how many % of the unit tests fully pass. So you can see things like essentially like fully completed tasks would show up like here at the 100% mark, but you can also look at like, for example, the median pass rate and many more things. And really, I think here you can very clearly see how different models perform. If you're interested in ProgramBench, we also have this graph interactively on the website. I think this is literally the most interesting thing about this benchmark, that we can do this graph. Now, cheating, I already mentioned that. This is one of the biggest challenges, I think, nowadays when developing benchmarks that are ambitious in terms of giving the agent a lot of freedom. One of the restrictions we made from the beginning was that we don't give the agent any internet access, because it could just look up the original project. But agents are now incredibly good at finding loopholes. So here, this was Sonnet 4.6. We had Sonnet 4.6, like it saw that it didn't get internet during the evaluation run. Like it saw that it didn't get internet while its agent was trying to solve the thing. But what it did was essentially speculating that when we evaluate it, like when we take its solution and evaluate it, that maybe the evaluation machine has internet. And then based off on that, and this is actually like a direct quote, like does the evaluation machine have internet? I think the answer is yes. It snuck in some code, within its submitted code that during evaluation, during the running of the unit test, it would go to the internet and download extra packages to use that dependency to pretty much make the problem trivial. So you can find the full, I think you can find the full trajectory in the blog from ProgramBench. But I think this is crazy that this happens. Like this behavior is oftentimes amplified when people do RL on benchmarks and models just learn to reward tag. So this is fun and challenging as a benchmark developer. Again, just shamelessly plugging here, ProgramBench.com. Can't cover all of these things here. But there's a lot of there's a pretty big FAQ section, including can tasks be fully solved? I think that's one of the critical questions for this benchmark. Why are the official scores so low? Have we considered other metrics? So for example, Anthropic, and a lot of people are using a different metric on ProgramBench that makes it look like they solve almost everything, even though that's not the conclusion that we have. So check it out. And yeah, that's it. 2 projects. There's CodeClash.ai if you want to learn more. There's ProgramBench.com. And if this was a live discussion, I would love to hear more suggestions about benchmarks or how we can overcome this initial problem that I pitched. That previously we've thought a lot about making AI solve specific tasks, but now we're more and more at the stage where we think about how can we evaluate what goals AI can accomplish.
Thank you so much, Kilian. And with that, any last words for the audience here at AGI House? Anything you want to see people build or use ProgramBench or CodeClash for?
Yeah, thank you so much for having me. This was so much fun. Yeah, I'm always excited to see benchmarks that are completely off the beaten track. Now the models are so capable, I think there's so much more that we can get these models to do, and it's going to be so much harder to evaluate them on. So I think benchmarking is one of the most rewarding things to work on right now. Very concretely, for ProgramBench, as I mentioned, if you work on a multi-agent scaffold and you want to really see a benchmark where it maybe outperforms a single agent, you can submit it to the leaderboard and we'll list you there. For CodeClash, if you're into games, we're always interested in expanding the section of competitions we have listed there. So that's also an interesting avenue if you want to contribute. And else, you can find me on Twitter or wherever, and I'm love to talk about new benchmarking ideas, etc.
That's awesome. Thank you again for being keynote speaker at Auto Research Build Day as well. And with that, thank you, Kilian.